This video, we will explain the Fourier series representation of a unipolar reverse sawtooth, or reverse ramp waveform. We will see how a non-sinusoidal signal can be expressed as a sum of sinusoids, how the waveform shape determines inharmonic components. This analysis is fundamental in signal processing and electronic systems. Here, we're going to derive the three Fourier series forms of a unipolar reverse sawtooth wave function: the exponential form, trigonometric form, and combined trigonometric form. Next, we're going to derive the root mean square, or RMS voltage. 3. We're going to use the MathCAD application to validate the derived Fourier series formula to graphical representation. So 4. We'll use MATLAB to view the spectral components of the wave. 5. We're going to use Multisim app in simulating an electronic circuit that will produce a square wave signal. And last, we're going to validate the circuit design through actual laboratory implementation. Now, we're going to derive the Fourier series forms of a unipolar reverse sawtooth wave function. So, we have the exponential form, trigonometric form, and combined trigonometric form. Here we have the unipolar reverse sawtooth, also called a negative ramp waveform. This signal is defined over one period, t, and then repeats periodically in time. Notice the two features of the waveform. First, there is a slow negative ramp where the signal decreases linearly from its maximum value down to zero. Second, at the end of each period, the signal undergoes a vertical rise, instantaneously resetting back to its maximum value. Because the signal is unipolar, it remains entirely above the zero axis, which introduces a non-zero average or DC component. This characteristic will directly affect the Fourier series coefficients. In the next steps, we will mathematically define this waveform over one period and use that definition to derive its Fourier series representation. This will allow us to express the reverse sawtooth as a sum of sinusoidal harmonics. You may pause the video at any time to closely examine the waveform shape and its periodic structure, as this understanding is essential before moving on to computations. Now that we understand the shape of the unipolar reverse sawtooth waveform, we can construct its mathematical expression over one period. Observing the waveform, the signal starts at its maximum value at limit t equals 0 and decreases linearly until it reaches 0 at t equals big T. This behavior corresponds to a negative ramp. Because the waveform is linear within one period, we can define it using a single piecewise expression. So this function is written as f of t is equal to a times the quantity of minus t over big T for t greater than or equal to 0 and less than big T. At t equals 0, the function evaluates to f of 0 is equals to a, which represents the peak value of the waveform. At t equals to big T, the function becomes f of big T equals 0, corresponding to the bottom of the ramp. This piecewise function fully describes one cycle of the unipolar reverse sawtooth. By extending this function periodically, we obtain the complete waveform shown earlier. With this time domain expression established, we are now ready to proceed with the Fourier series derivation. We now express the waveform using the trigonometric form of the Fourier series. The standard trigonometric Fourier series is given by f of t is equals to a sub-zero plus the summation from k equals to 1 to infinity of the quantity a sub k cosine k omega naught t plus b sub k sine k omega naught t. This representation allows any periodic signal to be written as a combination of cosine and sine function at the integer multiples of the fundamental frequency omega naught. To fully describe our unipolar reverse sawtooth waveform, we need to determine three sets of coefficients: the DC components a naught, the cosine coefficient a sub k, and the sine coefficient b sub k. Each coefficient captures a specific contribution of the waveform's shape to the overall signal. In the next steps, we will compute these coefficients using the piecewise function defined earlier. We begin by finding the coefficient A0, which represents the average or DC value of the waveform. The formula for A0 is given by A0 equals to 1 over big T times the integral from 0 to big T f of t dt. Next, we substitute the expression of the unipolar reverse sawtooth that we defined earlier. F of t is equals to A times the quantity 1 minus t over big T. This gives A naught equals to 1 over big T integral from 0 to big T of A times the quantity 1 minus t over big T dt. We now integrate the expression inside the brackets. After integration, we obtain A0 is equal to A over b t times the quantity t minus t squared over 2 big T evaluated from 0 to big T. Evaluating at the limits when t is equals to big T and t equals 0, the expression simplifies to A0 equals to A over big T times the quantity of big T minus big T over 2, which finally results in A0 equals A over 2. This confirms that the average value of the unipolar reverse sawtooth waveform is half of its peak amplitude. You may pause the video here to review the integration steps before we proceed to the remaining Fourier coefficients. Now we derive A sub k, the cosine coefficients. Here's the formula. A sub k is equal to 2 over big T times the integral from 0 to big T of f of t times cosine k omega naught t dt. We let u equal a times the quantity 1 minus t over t. Taking the derivative, du becomes negative a over t dt. Note the derivation of constant a is 0 and the derivative of minus a t over big T is minus a over big T. We let dv equal cosine k omega naught t dt. Integrating that v becomes 1 over k omega naught times sine k omega naught t. A sub k 2 over times 2t times that quantity 8 times 1 minus t over t times sine k omega naught t over k omega naught evaluated from 0 to t minus the integral from 0 to t of sine k omega naught to t over k omega naught multiplied by negative a over t dt. At t equals big T, sine of k times 2 pi t over t simplifies to sine of 2 pi k, which is 0. At t equals 0, sine of 0 is 0. The whole boundary term is 0. So now evaluate the integral term. The remaining integral is of a sine function over a full period integral of sine dt, which is always 0. Now we derive the bk, the sine coefficient. It is b sub k is equal to 2 over big T times the integral from 0 to big T of f of t sine k omega naught t dt. We let dv equal sine k omega naught t dt, integrating that v becomes negative 1 over k omega naught times cosine k omega naught t. Note, this negative sign is the most common place to make a mistake. The integral of sine is negative cosine. So to apply the rule, it is b sub k equals 2 over t times the quantity negative a times 1 minus t over t times cosine k omega naught t over k omega naught evaluated from 0 to big T. minus the integral from 0 to t of negative cosine k omega naught t over k omega naught multiplied by negative a over big T dt. So for step 4a, the boundary term uv, at t equals big T, negative a times 1 minus 1 equals negative a times 0 equals 0. At t equals 0, negative bracket, negative a times 1 minus 0 times cosine of 0 over k omega naught equals negative bracket, negative a over k omega naught equals positive a over k omega naught. So the boundary part gives us a over k omega naught. The remaining integral is the integral of cosine k omega naught t dt over a full period 0 to t. Just like with the sine function earlier, the integral of a cosine wave over a full period is 0. For step 4c, we combine. B sub k is equal to 2 over big T times the quantity A over k omega naught. Substitute omega naught equals to pi over big T. B sub k equals 2 over T times A over the quantity k times 2 pi over T, which simplifies to 2A over 2 pi k, which equals A over pi k. Now for the final solution, we substitute the coefficients back into its main equation. F of t is equals to a over 2 plus the summation from k equals 1 to infinity of the quantity 0 times cosine plus a over pi k times sine of 2 pi kt over t. For the final equation, f of t is equal to a over 2 plus the summation from k equals 1 to infinity of a over pi k times sine of 2 pi k t over big T. From our previous derivation, we established the trigonometric coefficients for the following ramp. Big A sub 0 is equal to a over 2, big A sub k is equal to 0. Big B sub k is equal to a over pi k. The relationship between the forms is c sub k is equal to 1/2 times the quantity of a sub k minus j times b sub k. C sub 0 is equal to a sub 0. Now we calculate the exponential coefficient c sub k. We calculate c sub k, or the average values in the correlation c naught is equal to a naught. C naught is equal to a over 2. Calculate c sub k, which are the harmonics. Substitute a sub k, which is 0, and b sub k equals to a over pi times k into the relation formula. C sub k equals to 1 over 2 times the quantity of 0 minus j a over pi k. C sub k is equals to negative j a over 2 pi k. So since negative j is already 1 over j, this is often written in cleaner form, matching the first slide, which is c sub k equals to a j 2 pi k, for k is not equal to 0. Third, the final exponential equation, the general form of the exponential Fourier series, is x of t equal to the summation from k equals negative infinity to infinity of c sub k times e raised to the power of j k omega naught t. Substituting are calculated c naught and c sub k values, where omega naught is equal to t pi over t. So x of t is equal to a over 2 plus the summation from k equals negative infinity to infinity, where k is not equal to 0, of a over j 2 pi k times e raised to the j 2 pi k t over t. The combined form is defined as x of t equal to c sub 0 plus the summation from k equals 1 to infinity of 2 times the magnitude of z sub k times cosine of the quantity k omega naught t plus the theta sub k, where c naught, the dc component, same as a naught, and 2 ck sub k, the peak amplitude of the kth harmonic. Theta sub k is the phase angle of the harmonic. Now we use the values we already derived. A naught equals to a over 2, a sub k is equals to 0, b sub k is equal to a over pi k, and ck is equals to negative j a over 2 pi k, which is the complex coefficient. The amplitude 2 c sub k, we need the magnitude of the complex coefficient c sub k. So c sub k, absolute number c sub k is square root real number squared plus imaginary number squared, which is c sub k is equal to square root of 0 squared plus negative a over 2 pi k squared, which is a 2 pi k. So now we multiply 2, which is the amplitude, 2 times a 2 pi k is equal to a pi k. The phase is the angle of the complex coefficient c sub k. C sub k is equal to 0 minus ja 2 over 2 pi k. On the complex plane, a purely negative imaginary number lies on the negative vertical axis. Angle is negative 90 degrees or negative pi over 2 radians. Alternatively, using the standard conversion from sine over cosine, pi k is equal to arc tangent minus bk over ak equals to arc tangent negative infinity, which is negative pi of 2. So for the final equation, substituting these values back into the previous equation, is x of t equals to a over 2 plus summation k 1 to infinity a over pi k cosine 2 pi kt over t minus pi 2. This confirms that the signal is made up of cosine waves that are shifted by negative 90 degrees, which turns them into sine waves, matching your earlier results. In summary, these are the different Fourier series of unipolar reverse sawtooth or ramp wave function: the trigonometric form, the exponential form, and the combined trigonometric form. So now we're going to derive the root mean square, RMS voltage of the signal. The RMS formula, the definition of the root mean square value for a period signal x of t with period t, is V sub RMS is equal to the square root of the quantity 1 over big T times the integral from 0 to big T of x of t squared dt. So now we're going to substitute the signal equation. Recall the equation for the falling ramp sawtooth and signal, which is x of t is equal to a times the quantity of 1 minus t over big T. Substitute this into the RMS formula, which is V sub RMS is equal to the square root of 1 over big T times the integral from 0 to big T of the quantity a times 1 minus t over t all squared dt. And then we're going to put the constant amplitude a squared out of the integral. So which is now V sub RMS equal to the square root of a squared over big T times the integral from 0 to big T of the quantity 1 minus t over t squared dt. Now we set u equal to 1 minus t over t, taking the derivative du equals negative 1 over t dt, which means dt is equal to negative t du. But we have to substitute. We do the substitution when t is 0 u becomes 1. When t is big T, u becomes 0. So I equal to the integral from 1 to 0 of u squared times negative t du, which simplifies to negative t times the integral from 1 to 0 of u squared du. Now we flip the limits to remove the negative sign. So now it's I equals to big T times the integral from 0 to 1 of u squared du. Now we evaluate the simple power rule. I is equal to T times the quantity u cubed over 3 evaluated from 0 to 1, which equals T times 1/3 minus 0, which simplifies to T over 3. So for the final calculation, we substitute the result of the integral T over 3 back into the main RMS equation. VRMS is equal to square root of A squared over big T times big T over 3. Now we cancel the T terms. It becomes square root of A squared over 3. And so VRMS is now equal to A over square root of 3. But we substitute A, which is the 5 volts, now 5 over square root of 3. Next, we're going to use MathCAD application to validate the derived Fourier series formula through graphical representation. Now this slide shows the time domain definition, Fourier reconstruction, and graphical comparison of the unipolar reverse sawtooth waveform. Now let's go through it step by step. At the top left, we define the parameters used in the simulation. The amplitude is set to A is equal to 5, the period T is equal to 1, and the fundamental angular frequency is W is equal to 2 pi over T. The number of harmonics used to reconstruction is N equal to 200. Next, we define the time vector T, which runs from 0 to 3 periods with a small step size. This allows us to clearly observe the waveform repetition. The function T defines the original unipolar reverse sawtooth waveform. The floor function enforces periodicity, while the linear term creates the slow negative ramp within each period. Below that, S of T represents the trigonometric Fourier series reconstruction. It consists of the DC term A over 2 and summation of the sine harmonics weighted by 1 over k. As more harmonics are included, the reconstruction signal more closely resembles the original ramp. The next expression shows an equivalent phase-shifted cosine form, which is mathematically identical but written in a different trigonometric representation. At the bottom, we express the waveform using the exponential Fourier series. Here, the signal is written as the real part of a sum of complex exponentials, where each term corresponds to a harmonic component with an imaginary coefficient. On the right-hand side, the plot compares the original waveform f of t with its Fourier approximation S of t. The close overlap between the two confirms the correctness of the derived Fourier series. Any small ripples near the discontinuities are due to the finite number of harmonics and are an example of the Gibbs phenomenon. You may pause the video here to inspect the equations and observe how the mathematical expressions translate directly into the reconstructed waveform. Now this slide shows the MATLAB implementation of the Fourier series for the unipolar reverse sawtooth waveform, including both the time domain reconstruction and the frequency domain spectrum. We begin by defining the constants. The amplitude is set to A, 5 volts, the period T is 1 second, and the fundamental frequency is f naught, which is equal to 1 over big T. We choose N as 200 harmonics to obtain a smooth waveform reconstruction. A high sampling frequency is used to accurately represent the signal, and the time vector is defined over 3 periods so we can clearly observe the periodic behavior. Next, we initialize the signal with its DC offset. From our Fourier derivation, we know that the average value of the waveform is A over 2, so we start the signal from this constant term. We then add the harmonic components using a loop. Each iteration computes one sine harmonic using the coefficient a over pi k, multiplied by sine 2 pi kt over t. This is exactly the trigonometric Fourier series derived earlier. As the loop runs, each harmonic is added to the total signal, gradually constructing the reverse sawtooth waveform. After generating the time domain signal, we compute the frequency spectrum. Here we calculate the magnitude of the first few harmonics using the same Fourier coefficients. This allows us to visualize how the signal's energy is distributed across frequency. The top plot shows the reconstructed waveform in the time domain. As expected, it closely matches the original unipolar reverse sawtooth with the small ripples near the discontinuities due to the finite number of harmonics. The bottom plot shows the frequency spectrum. The decreasing amplitude of the higher harmonics follows the 1 over k relationship, which is characteristic of ramp waveforms. Together, these plots confirm both the mathematical derivation and the numerical implementation of the Fourier series. You may pause the video here to examine the equations translate directly into MATLAB code. This figure shows the final result of the Fourier series constructed of the unipolar reverse sawtooth waveform. The top plot displays the waveform in time domain. The signal is generated by summing the first two sine harmonics along with the DC component. As shown, the reconstructed waveform closely follows the ideal reverse sawtooth shape, exhibiting a slow linear decrease and sharp vertical reset at the end of each period. Small oscillations near the discontinuities are visible. These are expected and are caused by the finite number of harmonics used in the reconstruction. This effect is known as the Gibbs phenomenon. The bottom plot shows the frequency spectrum of the waveform. Each vertical line corresponds to a harmonic component at an integer multiple of the fundamental frequency. Notice that the amplitude of the harmonics decrease as frequency increases, following an inverse relationship with harmonic number. This 1 over k decay is a key characteristic of ramp and sawtooth waveforms. Together, these plots confirm that the derived Fourier series accurately represents both the time domain shape and the frequency domain behavior of the unipolar reverse sawtooth signal. This concludes the Fourier series analysis and simulation of the unipolar reverse sawtooth waveform. This slide shows the Falstad circuit simulation used to physically generate a waveform similar to the unipolar reverse sawtooth discussed earlier. At the core of the circuit is a 555 timer IC configured to operate as a timing and waveform generation circuit. The capacitor connected to the threshold and trigger pins is the key energy storage element. As the circuit operates, this capacitor charges and discharges through the surrounding resistor network. The resistor values are chosen such that the capacitor discharges slowly, producing a nearly linear negative ramp, and then resets quickly, resulting in a sharp vertical rise. This behavior closely matches the reverse sawtooth waveform analyzed using Fourier series. The transistor and additional resistor modify the effective charging and discharging paths, allowing finer control of the slope and timing of the ramp. The output is taken from the 555 timer's output pin, while the ramp waveform itself can be observed directly across the capacitor. This simulation demonstrates an important point. The reverse sawtooth waveform is not just a mathematical construct. It can be generated using practical electronic components, and its behavior directly corresponds to the time domain function and Fourier representation derived earlier. By comparing this circuit-generated waveform with the Fourier series reconstruction, we see how mathematical signal analysis connects to the real-world circuit implementation. This figure shows the actual signal output obtained from the circuit simulation. The waveform clearly exhibits the characteristics of a unipolar reverse sawtooth, with a slow linear decrease followed by a rapid reset at the end of each cycle. The measured peak voltage is approximately 3.25 volts, and the signal operates at a frequency of about 2.5 kHz. as determined by the resistor-capacitor network. Because the waveform remains above the 0 volts, it contains a DC offset, which is consistent with the A over 2 average value derived earlier in the Fourier series analysis. The near linear slope of the falling edge indicates that the capacitor is discharging at an almost constant rate, while the sharp rise corresponds to a fast discharge path controlled by the switching elements in the circuit. This measured waveform closely matches both the ideal piecewise model and the Fourier series reconstruction, confirming that the mathematical analysis accurately predicts the behavior of the physical circuit. This completes the link between theory, simulation, and practical signal generation. Now we're going to validate the circuit design through actual laboratory implementation. So we're going to use the components resistor, capacitor, PNP transistor, and 555 timer. This breadboard circuit is the physical implementation of the reverse Sawtooth generator, confirming that the waveform derived analytically can be produced in hardware. Now you can see in this picture is the oscilloscope confirms the generation of a unipolar reverse Sawtooth waveform that agrees with theory, simulation, and Fourier analysis.